When looking in aviation history books, you can see the importance of NASA's Dryden Flight Research Facility. The list of flight accomplishments at Dryden is long as we have searched for ways to improve flight. In the early days, NASA, or the National Aeronautics and Space Administration, was known as NACA, the National Advisory Committee on Aeronautics. Engineers from the NACA facility at Langley, Virginia, were lured here in 1946 because of the vast, wide-open spaces in which to test aircraft. One of the earliest vehicles tested here was the first to reach supersonic speeds, the XS-1. We take our name from Dr. Hugh Dryden, one of these early aviation pioneers. Dryden is located 90 miles north of Los Angeles, California, in the Mojave Desert. The clear skies, relatively sparse population, wide open spaces, and dry weather make it the perfect place for aeronautical flight testing. From Dryden, pilots have access to over 20,000 square miles of restricted airspace over a portion of the western United States and off the west coast. The NASA facility is on Edwards Air Force Base on the edge of Rogers Dry Lake Bed. This is a 44 square mile smooth flat surface, providing supplemental landing runways to the hard runway complex at Edwards. Many of the early X-series aircraft paved the way for even more productive and successful experimental aircraft, like the X-15. It flew at Dryden between 1959 and 1968. Experimental test pilots flew it at Mach 6.7, or over 4,500 miles an hour, and reached peak altitudes of 350,000 feet, or over 66 miles high. During the decade it flew, the X-15 program provided information which benefited the aircraft and space industries for many years to come. The program produced over 750 technical reports on the results of the X-15 experiments. Another breakthrough here was the first flight of the lifting body spacecraft configuration. The first of these lifting bodies, the M2F-1, was unpowered and first towed into flight behind a car racing up and down Rogers Dry Lake Bed, and later behind a C-47 aircraft. Another was the HL-10 lifting body. It's on display just outside the Dryden main front gate. These are two of the 5 lifting body designs that led to development of our space shuttle fleet. Tests at Dryden helped prove certain theories about spaceflight were correct. For example, man could fly a vehicle into space, re-enter the Earth's atmosphere, maneuver the craft, safely land it back on Earth unpowered, and reuse the spacecraft. Through the years, some rather unusual-looking vehicles were tested at Dryden and helped benefit the space and aviation industry. For example, this, the Parasev. It was a space-age kite engineers thought could be used in place of parachutes that were used to recover America's early spacecraft. In early 1962, the Parasev was tested at Dryden, pulled into flight behind a car racing down the Dry Lake Bed. The Parasev was never used for this purpose, but the technology developed into modern-day paragliders and hang gliders. Another alien-looking project tested at Dryden was the Lunar Landing Research Vehicle, LLRV. Nicknamed the Flying Bedstead, the LLRV was designed to create gravitational conditions similar to what was thought to exist on the Moon. This helped train our Apollo astronauts for what to expect when they landed on the Moon in the 1960s. Two highly modified F-8 aircraft tested at Dryden in the 1970s proved to be extremely valuable. One was testing digital fly-by-wire theory. This is where computer systems replace mechanical control systems on an aircraft. Fly-by-wire systems reduce aircraft weight, take up less space than mechanical systems, and allow for advanced aircraft configuration designs. A supercritical wing was installed on Dryden's other F-8 aircraft. The supercritical wing has an airfoil or wing shape which delays the formation of shock waves as the aircraft approaches the speed of sound. The supercritical wing allows an aircraft to cruise at higher speeds using less fuel, making it much more efficient. Many of today's military and commercial aircraft incorporate fly-by-wire and supercritical wing technologies. Also in the 1970s, NASA flew a pair of YF-12s frontrunners of the SR-71 in a lengthy research program to study a wide range of disciplines associated with high-speed, high-altitude flight. Today, NASA is flying the Blackbirds once again, using the former Air Force reconnaissance aircraft to conduct experiments to benefit future high-speed aircraft. A more recently completed test project at Dryden is the X-29. This forward-swept wing concept dates back to Germany in the 1930s. The design just wasn't practical back then because stronger, lighter materials that were needed to keep the forward-swept wings from ripping off in flight were just not available. The Advanced Research Project Agency, U.S. Air Force, NASA, and the Grumman Corporation tested the forward-swept wing vehicle at Dryden through 1991. Over 374 test flights, many exploring controlled high angles of attack, were conducted. During 1992, NASA and the Air Force's Wright Labs used the aircraft for vortex flow control experiments. These showed that by injecting nitrogen gas into the plane's nose vortices gave the aircraft added control at high angles of attack. Now let's take a look at some of the NASA Dryden family and their day-to-day activities. Constant close coordination is necessary before, during, and after every research flight. The crew briefing is a chance for all the major players like the pilot, program manager, chief engineer, operations engineer, and director of flight operations research to get together for a final review and coordination before each flight. The key person at the crew brief is the research pilot. The pilot has to be aware of all the objectives the researchers and engineers want to meet, and be able to translate the paper requirements needed by the people on the ground into useful, actual flight test results. Dryden's two fully equipped flight control rooms are used for efficient data acquisition and monitoring each research mission. These control room occupants are a highly specialized team coming together from various organizations within Dryden for a specific flight. On most missions at Dryden, there's a primary or mission controller who's usually another one of our pilots. There's also an operations engineer responsible for monitoring the aircraft systems and providing the mission controller with all the vital data needed during normal or emergency procedures. Other staff members are engineers responsible for monitoring the flight's experiments and ensuring the data they want to acquire is obtained. In addition, program management personnel take an overview of the entire operation and factor in variables like the weather, range situation, and time. A key component in the flight test data acquisition process is the data analysis facility. Here, all flight test data is recorded, stored, and transmitted to other NASA and industry sites for use in various flight research programs. Here, raw flight test data is collected, formatted, and printed for use by the different flight test teams. Many detailed aircraft tests are conducted under one roof at Dryden's Integrated Test Facility, or ITF. Today's modern aircraft contain many highly interdependent systems involving flight controls, structural dynamics, propulsion, aerodynamics, and avionics, all requiring close coordination for accurate data acquisition. In this one-of-a-kind national resource, researchers can simultaneously test all of the aircraft systems by simulating actual flight. Engineers, as well as research pilots, can control the flight simulation and monitor data that's also being recorded for later analysis. Also at Dryden's ITF, researchers conduct ground vibration testing, perform routine aircraft maintenance, and verify and validate flight software, all in this one location. Another test area is the Flow Visualization Facility, or water tunnel. Here, researchers take standard off-the-shelf model airplanes and modify them with tubing so they can inject different colored dyes into the water. The dyes flowing through the water act very similar to the air around an aircraft in flight. Researchers can quickly, accurately, and inexpensively illustrate actual aircraft flight conditions to better understand airflow around the aircraft and to help locate instrumentation on future aircraft. We probably receive much outside attention as a landing site for the Space Shuttle orbiter fleet. The 3-mile-long hard surface runway and the extra flat, smooth surfaces provided by Rogers Dry Lake Bed make it an ideal place for landing a space shuttle with a heavy payload or because of bad weather at the Kennedy Space Center, Florida. When landing at Dryden, the orbiters are deserviced and mounted on top of NASA's 747 shuttle carrier aircraft for return to the Florida launch pad. As you have seen, Dryden's past is full of many valuable aeronautical achievements. The present-day test projects are proving to be very important as well. The latest experimental, or X-Series project, is the X-31. It's an international effort with participation from government and industry groups in Germany and the United States. High angles of attack, performing rare turn maneuvers, and thrust vectoring have been tested here on the two X-31s. Thrust vectoring means changing the direction of the exhaust from the jet engines as a way of improving the aircraft's performance. Some major accomplishments in the X-31 program: sustained 70 degrees controlled angle of attack, and the J-turn, or the Erbst maneuver. During this J-turn maneuver, the pilot is flying at 70 degrees controlled angle of attack and will sharply turn the aircraft, basically ending up going in the opposite direction. Dryden's F-18 HARV, or High Alpha Research Vehicle, continues to provide data on agility, handling qualities, control law evaluations, and surface pressure surveys. The HARV is a standard F-18 aircraft that's been modified with 3 spoon-shaped paddles per engine to vector or move the exhaust thrust for better control at high angles of attack. Results of this research will help shape future military aircraft. The HARV also explores 60 and 70 degrees controlled angle of attack and provides researchers with the ability to more accurately predict the flight characteristics of future jet fighters. Our highly modified F-15 was used recently to test digital electronic engine and flight control systems. These will help future military and commercial aircraft fly more safely and efficiently. Computer software on board our F-15 throttles the engines to the lowest possible power settings and sustains supersonic flight. Another test on the F-15 high deck, or highly integrated digital electronic controlled aircraft, is a software system which compensates for control system failures, which would render most normal aircraft uncontrollable. This propulsion-controlled aircraft software system gives the pilot the ability to safely steer and land the aircraft using only computer control of the engines. This will prove to be a valuable piece of equipment to have on an aircraft in the future. Our B-52 launch aircraft is the oldest active B-52 in the country. This vehicle has launched X-15s and the experimental lifting bodies and has a long list of other accomplishments. The drag parachute system used on today's space shuttle was tested behind the B-52. The chute reduces tire and brake wear on our orbiter fleet. The B-52 is also used to launch Pegasus, a commercially developed 3-stage rocket booster that puts smaller payloads into orbit for less cost than ground launches. NASA's Convair CV-990 has been modified to test loads and stress points on space shuttle landing gear, tires, and braking systems. This is part of the continuing effort to upgrade and enhance the space shuttle landing capabilities. The CV-990 touches down with its own landing gear. Then a shuttle landing gear strut is hydraulically lowered to the runway to simulate shuttle touchdown conditions. This gives engineers a better way to measure and isolate stress points and loads, making the shuttles safer. In support of future high-speed civil transport, NASA researchers are using a modified F-16XL to study laminar or smooth airflows. By smoothing the airflow, the aircraft flies more efficiently at all speeds. The porous titanium glove installed in the cranked arrow wing of the F-16XL induces this smooth airflow. And by monitoring the airflow during flight, researchers at NASA's Langley and Dryden facilities can determine how laminar airflow is affected at different flight conditions. Dryden also continues to fly the SR-71 Blackbird as a high-speed, high-altitude research platform. The SR-71 and our F-16XL conducted acoustic studies to determine ways to reduce noise from future high-speed aircraft. Dryden also is conducting tests for the Jet Propulsion Laboratory in Pasadena. Highly sensitive ultraviolet instruments for astronomical studies were carried into the atmosphere aboard the Blackbirds. Now to welcome you to the Dryden Flight Research Facility, Director Ken Saleh.
Aviation has played a major role in this country's economic growth and security. Civil aircraft carry business people, tourists, families, students, critical equipment, mail and cargo. A strong aviation infrastructure is vital for this nation's competitiveness and national security. The sale of civil transports, for example, is a major positive contributor to the balance of payments. Military aircraft keep the peace, and when they're called upon, force the peace. We're celebrating the 90th anniversary of the Wright brothers' first flight at Kitty Hawk. A scant 12 years later, in 1915, the National Advisory Committee for Aeronautics was formed, and the United States began aeronautical research. NASA continues this proud tradition of aeronautical research by pioneering new concepts, transferring technology to the U.S. industry, and by solving problems when they occur in air transportation. NASA's ultimate objective is to assure that U.S. aircraft have superior performance, are affordable to own and to operate, and are safe. NASA works in partnership with the U.S. industry, the Department of Defense, universities, and aircraft operators. Here at NASA Dryden, we explore the realm of flight, turning ideas into reality and making discoveries every day that are used for the design of future aircraft. Aeronautical research and development is really an investment in the future. At NASA, we intend to work hard for you, the American taxpayer, to ensure a large return on that investment.